right? Okay, so I think what you're trying to ask me is that here we have a case where we had a negative delta H and we have a negative entropy, right? And so when they're both the same, I said it's temperature dependent, right? Whether it's spontaneous or not, right?
Right, and then we got
So here we actually did the calculation at a particular temperature. And so we were able to decide that, okay, since we know the exact temperature, we can make the calculation, and it is this value, it is negative, it's a spontaneous reaction. Yes?
So the question would be like calculate the whatever at 298 Kelvin?
Yes.
Okay, so it would tell you the temperature.
Right.
Okay, I'm just
Now
trying to
the
figure
only
out
thing
what
that,
the
now let's go back to my general, okay? So if we have negative G is equal to delta H minus T delta S, okay? And I told you that enthalpy is less than 0, so my delta H is less than 0, and my entropy is less than 0, okay? Now, you could be asked, will this be spontaneous at low temperatures or at high temperatures, okay? Just a general question. Is it more likely to be, right? Okay? And so then you would have to say, okay, if this is negative, this is a negative times a negative makes a positive, right? So it's always taken a little bit off of this, right? And so you would say that in general, it's more likely to be spontaneous at a, what? Low temperature and become non-spontaneous at a high temperature, right? Because as temperature goes up, this positive part of it gets bigger and bigger and bigger and bigger and bigger and bigger until finally it's bigger than this. So you kind of have to know, here we had a specific set of numbers we were using to calculate. Here we have just general questions. Okay, so you can, when those signs are the same, you can be asked either specific questions or general ones. Okay? Is that the answer to your question, or was I answering the wrong question?
I answered most of it, but could you hit the arrow again so I can
Hit the arrow again.
see?
Yeah.
So that's enthalpy driven.
Right.
And we have a negative delta G.
Right.
And we're
Negative
calling-
delta G tells us it's spontaneous.
Okay, so we're calling it enthalpy driven because of delta S?
The delta S is negative,
Right.
which we've decided if we're looking at negative S only, negative delta S tends to mean a non-spontaneous process. Okay? So that's why we're calling this enthalpy driven, right? Now, if we picked a different temperature, it might be non-spontaneous. Okay? These two examples are just to show you examples of why we call it enthalpy driven or why we call it entropy driven.
Can we look again at the second example?
Sure. Can I just look at this part of it?
Yeah.
Okay. Now here, our delta H is positive, which we would say would tend to favor being non-spontaneous, right? However, this increase in entropy, which we say tends to favor spontaneity, is so large, but we have a negative sign here. When we're subtracting a positive, that's what makes it negative. Okay? So the overall delta G is negative, right? And we say it's, oh, I didn't put that part down. We say it's entropy driven because that's the part of those two variables in that particular example that tends to favor spontaneity, right? Okay. There's a hand up over here as well. Yes.
So, for the sake of like simplicity and putting this back to the table, the type 2 where delta H and delta S are both negative, then it'll always be enthalpy driven. And then if they're both positive and it's going to occur, then it'll be entropy. Okay.
No, it'll be, yes, entropy.
Okay.
Yep. Okay? Well, I'm glad you asked those questions because I understand it by using the negatives and the positives.
She worded it a lot better than me.
Well, no, there's no, and I just, so I'm glad you brought that up. Okay, so here, if we had the combustion of carbon, we could look up the value for the heat of formation. If you were told to look at a table in the back, this is what they want you to do. Again, note that the free energy of formation of an element in its standard state is 0. If we were to look it up in the table, this is the value for carbon dioxide. That would make the standard change in Gibbs free energy for this reaction equal to negative 394.4 kilojoules. And so the reaction is product favored as expected. Okay, now, people always forget about this. If we had iron oxide plus 3 carbons, we get 4 irons plus 3 carbon dioxides. I'll write down these numbers so you can see them. The delta H standard for the reaction is equal to plus 467.9 kilojoules. Our standard delta S of our reaction is equal to 560.3 joules per Kelvin. The delta G standard for the reaction is equal to 300.8 kilojoules. The reaction is reactant favored at 298 K. Alrighty? At what temperature does that reaction just change from being plus to being negative? All right, now, so we said, if you recall, when delta G is less than 0, we call that spontaneous. We said that when delta G is greater than 0, we it's non-spontaneous. All right, and when delta G is equal to 0, it's going to be what? At equilibrium. Now, here we have a delta G that's positive, right? What do we have to go through? What number do we have to go through to get to